Today I'm going to talk about entanglement-based quantum key distribution with high dimension encoding. And this is work done at MIT in collaboration with NIST and JPL. So first of all, I'd like to start by saying why we might be interested in high dimension encoding and what it means. So let's take a generic case of a CW down converter generating pairs of entangled photons. And typically, we actually run the system under what I call photon-starved conditions. What it means is that there are component losses and propagation losses, especially propagation losses, since we always want to have long-distance transmission. So that means that the number of pairs that would actually reach the detectors at Alice and Bob are fewer, much fewer than what you started with. Now, not only that, there are long recovery times for these detection systems. For example, they may be, it may take several tens of nanoseconds before, after it detects one photon, that it would take that long before they can actually measure the other one. So that means that the number that actually you detect by Alice and Bob are even fewer, okay, than you started with. And so given that conditions, what high dimensional encoding, in this case for the time of arrivals of the photons, is to pack as many bits in one photon to maximize your throughput. Okay? So this is not a new concept. This was actually proposed and demonstrated some time ago, what he called large alphabet encoding by John Howard. And let's take a look at a very simple case. Typically, the biphoton coherence time is of the order of, let's say, a picosecond. And if you think of a frame of 10,000 of these time bins, then you're talking about 10 nanoseconds, and you can pack as many as 13 bits per photon pair. And that means that you can, in principle, get as high as 1.3 gigabit per second. Now, if you have the same condition and you say, let's do binary encoding, then you can only get a tenth of a gigabit per second. So the question is that what are needed to do the high dimension encoding, in particular for time of arrivals of the photons? Some of these things are actually pretty standard for all kinds of QKD measurements. You need a very good source, entangled photons. You need very efficient detectors. Now, we don't actually need more detectors than you would need for, let's say, standard BB84. You need a very efficient error correction and privacy amplification. In particular, we actually use a multi-layer low-density parity check we designed specifically for this high-dimensional encoding. And then of course, you need security checks, right? And in this particular case, we have two implementations. One is using dispersive optics, and the other one using a single Franzen interferometer. Now, I'm not going to talk very much about security. I'm not the right person to talk about security. And however, if you are interested in the details, you can always go check out a couple of publications we did, one on dispersive optics last year, and the other one on using a Franzen interferometer earlier this year. What I want to say is that for both cases, we borrowed the technique, the security analysis technique for CVQKD and apply that to our high-dimensional QKD. The idea is that we are really doing continuous time, okay? But the measurement is actually discrete energy, single photon counting. So the idea is that we try to, using time of arrival and the frequency as the conjugate basis, okay? And then we try to relate the security measurements that we have to the time frequency covariance matrix, especially the frequency elements. And from there, we can actually bound Holavel's information of Eve. So in the case of the dispersive optics, the idea is very simple. It almost looks like a BB84. You can either do measurement in time basis, or you can do it in frequency basis. When you're doing in the frequency basis, all we're doing is that we put a negative dispersion on one side and then positive dispersion on the other side. Okay, just like what you do with BB84, you put HMV for one basis and then plus or minus 45 in the other basis. Okay. Now, in the case for a Franz interferometer, what we did was that we can either generate the keys in the time basis, or when we are doing the security dimension, we use a Franz interferometer, which is really a asymmetric Mach sender on each side. Okay, and I'll go back to that in a little while. So in both cases, we are using a source that is really efficient. We are using a PBKTB waveguide source, generating 10 million pairs per nanometer and per milliwatt. And we can couple the light into the single mode fiber very easily. These are orthogonally polarized light, so we can separate the signal and an idler very easily. And I'm not going to talk too much about the source itself. So let's go to the dispersive optics QKD protocol. And the protocol is very simple. You already saw, basically you choose a frame size that, after you do the measurements, you pick in the software, okay, the frame size you want, the duration, the bin duration that you want, and then when you do sifting, what you want is to pick a frame that has only one detection, okay? And of course, Alice and Bob have to have their timing synchronized. So what you have here is that you have a normal dispersion on one side and then anomalous dispersion on the other side. So again, the idea is similar to BB84. Okay, you have two mutual unbiased bases. When they're in the correct basis, then when you're doing the timing measurement, you will get a very narrow coincidence. And if you're in the wrong basis, well, you discard them, just like in BB84. And the idea is that when you are doing security check, if you are in the correct basis, any timing errors because of eavesdropping, you will be able to detect it, because now the correlation is messed up and then it gets broadened. And let me go to some results that we have done. So this is a schematic. So you have the down conversion source, couple the light into a single mode fiber that you separate the signal and idler. Signal goes into here. We use a passive beam splitter 50-50. It either goes to generation without any dispersive element, or it can go to a normal dispersive element, and then you detect that. And this is simply this one and what Bob dispersive element is just a pair of fiber back rating that are matched so that they have opposite dispersion. So this is what you get if you have the same basis in here, okay? That means that there's no dispersion on either side. We measured about 110 picosecond correlation time. This is compared with the detector timing jitter of about 100 picoseconds, so that's including that. If they both go through the dispersive elements, then we're measuring something a bit broader, 140 picoseconds. Part of it because the two gratings are not perfectly matched. But if you're in the wrong basis, or if this is one of those times that Eve is actually looking in, you will see that it can broaden significantly, and you can tell. So these are some of the measurements that we did. So if you look at the key capacity, that means that how many bits per photon or per photon coincidence you can get. You can write it down like this. You have the usual mutual information between Alice and Bob, which has to be multiplied by the reconciliation efficiency. And you subtract the label information that you obtained by your security measurements. And then in this particular case, we also, keep pressing the wrong button. And you also have to subtract the finite key correction, which in this case is actually quite small, as you will see. So what we're showing here is this as a function of the dimension. That means that how many bins per frame that you want to have, okay, as a function of that. And then these are the some of the calculated numbers versus the measure numbers. So the pink line or purple line is what you expect theoretically if everything is perfect. Okay, so that's just the log2 of the dimension, the Schmidt number. This gap is due to when I subtract the Eve's whole level information and also the finite key correction, okay, down to here. The big drop is actually from here to here, which is really due to the timing jitter and more importantly due to the multi-pair emission. In this particular case, we were driving the dyne converter a little bit too hard. Okay, so there's a lot of multi-pair events coming up, and that causes the big drop in here. So after we correct that, you can see it actually matches quite well with what we actually are able to obtain, which is we're at the peak for a frame that has 256 bins, so that's 8 bits per frame. We can get a little bit over 3 bits per coincidence. So the proper metric that you're interested in is probably who cares about how many bits per photon that you can get. Just tell me what is the key rate that you can get. What is the throughput, right? So if we do that, then this is a plot of, we actually change the driving power for the dyne converter, so that implies that it changes the pair generation rate. And also the other side is the frame size. Now, it actually turns out that the maximum throughput does not always occur. In fact, it almost never occurs at the point where you have the maximum key capacity. And that actually makes sense because if you think about it, up to a certain point, if you increase your frame size by a factor of 2, you gain 1 bit. But the number of frames per second, you actually lose by a factor of 2. That's not a good trade-off. Okay? So in fact, in here, we get about a little bit over 270 kilobit per second in the secure key rate. But at that point, the secure key capacity is about a little bit over 2. So let's go to the other protocol, which is using a single Francis interferometer. You know, Francis interferometer has been around for a long, long time, and typically you use that to check the quality of your time bin or time energy entanglement. And in this case, it also that actually basically measures the frequency correlation of the 2 photons, okay, of the biphoton state. And so that means that if there is any degradation to the frequency correlation, let's say by a certain amount of epsilon, your visibility of the Francis would drop by the same amount. So that means that you really want to have a high visibility so that you can detect any kind of small amount of the frequency disturbance to your correlation, in particular, if it is by Eve. Okay? So the problem with that is that there are 2 typical limitations to a high visibility Francis interferometer, even when Eve is not around. And one is that there is multi-pair event. So you can do that if you lower your power a little bit, just don't crank up too high. The second one is there's a differential dispersion between the long and short path, this long and short path on each side. That small amount of dispersion would cost you. So in our case, we did both. We take care of the differential dispersion by compensating the dispersion of this side by putting the opposite dispersion on the other side. And also we drive it not too hard. So this is actually what we did some time ago. We obtained something like 99.6%. And you can clearly see that if you drive it too hard, this is the pair generation per coincidence window. The visibility just drops. Okay, so you don't want to do that. Now, when we are doing the experiment for the QKD, we're actually using nanowire detectors, and we were able to get 99.8% for the measurement. Oops. So this is a schematic, very similar to the dispersive optics system. Light comes in, goes into the fiber, separate into signal annihilator that goes to Bob and Alice and Bob. The only difference is that we are now using something that's a little bit more optimized for the key generation. This beam split is 90% going to the key generation and 10% going to the Francis interferometer. Same thing for Bob. Okay, so here are the results. Let's look at the green. The green is the key capacity, and you can see that it rises rapidly as a function of the frame size, and it peaks around when the frame size is 12 bit per frame. So that means it's 4,096 time bins per frame. And we obtain something that is as high as 8.8 bits per coincidence. Okay? And the red is the throughput, which we care about. And again, it rises sharply as we increase the frame size. And then it peaks when the frame size is about 10 bits per frame. So that's 1024. Now you can clearly see that as you increase the frame size more, the throughput actually drops significantly. And then the peak location for the key capacity and the throughput are obviously not the same place. And the thinking here is that you can increase it as high as possible until a couple of things will limit you. One is that your multi-pair events within that frame size is now too high. Okay? In this particular case, around here is of the order of 1 per frame. So anything more than that, you obviously don't have a lot of single photon event in each frame. The other thing is that you really want to wait, increase it until is a little bit larger than the recovery time of the detector. Okay, and then that you basically, that's where the peak. Now we can compare with the best we found, the entanglement-based QKD measurement by Salinger group. Clearly, you cannot have more than 1 bit per coincidence. In fact, their number is about a third, and the key rate is about 14.5 kilobit per second. In our case, we're able to reach about 7.1 megabit per second, and at that point, the key capacity is still 7.5 bits per coincidence. Now, we can also measure that to look at the key capacity and the throughput as a function of transmission distance. We're now to about 20 kilometers of fiber between Alice and Bob, and you can see that the key rates obviously drop, and that's just because of loss. More interestingly, you see that the key capacity remains more or less the same, about 7 bits per photon coincidence, and part of it is because basically it says that the high dimension encoding does not degrade, does not matter if you have losses. The other thing is that the Francis interferometer does not degrade over long distance, and that's very important because then you can keep bounding the EVE information as best as you can. So in summary, we have shown you a couple of implementations of the high-dimensional QKD systems. One is using a dispersive optics to bound EVE's information to do security check, and the other one is using a simpler, and in this case, because of the lower losses associated with it, that gives you a higher rate using a single Francis interferometer. Both are actually capable of doing multi-bits per coincidence, and also if we optimize dispersive optics, we can also go above a megabit per second key rate. So finally, I'd like to acknowledge the people who did all the work. That includes the people at NIST and JPL for the detector work. But I want to point out Tian Zhang, who actually did most of the work in the Francis interferometer QKD system. He is now a postdoc at Caltech, and Kathleen Lee, who did the counterpart, the dispersive optics measurement. So thank you very much.
maybe you told that and I didn't follow, but I have the impression that your time statistics are highly non-Gaussian and that you are using covariance matrix to bound the whole level information to Eve. And all the bounds are restricted to Gaussian stuff, so.
For the dispersive optics one, well, the proofs were done without requiring the statistics is Gaussian. So dispersive optics is actually secure against, well, let's say the coherent attacks. However, the single Franzen interferometer is restricted to a Gaussian collective attack simply because, so the original proof, we actually have what we call a conjugate Franzen interferometer, in which is almost like a Franzen, except the equal path length, and we put a frequency shifter in there. That actually would replace the time basis. So, okay, so you have a frequency basis and a time basis. In that case, is again secure against any attack. But in the single Franzen case, we actually couldn't do that without that. And but if we limit it to just a Gaussian attack, then yes. So for the single Franzen interferometer, it has to be is not secure against arbitrary attacks. So.
Hi, nice results. I saw the system efficiencies were like of Alice and Bob were around 7 or 10%. So are these due to optical losses from these dispersive elements, or is it something else?
I couldn't hear what you said because the sound was very muffled.
Okay, so the system efficiencies of Alice and Bob in one of the slides were mentioned around 10% or lower. So is it due to the optical losses?
Yeah, it's optical losses. Even though both are using, for example, even though both are using waveguide entanglement source, there are two different systems and they have different coupling efficiency into the single mode fiber. So the dispersive optics one has a little bit more losses, and also we're using a number of fiber optic components in there. They're a little bit lossy, but they're using the same detector. So the detector is the same, but yes, there are additional losses in that case.
So I have a question for the second scheme. Your Franzen QKD scheme, it is possible to demonstrate such scheme with a pulsed pump laser, I mean.
Well, depends on how pulse you want it to be. If you want it to be a discrete pump, like pulses, then is no longer a continuous time. And so our security check doesn't apply to that. However, if you talk about a pump that has a very long, it's a pulse, but it's a long coherence time that matches with the frame size, then that's okay.
So I mean, to match the group velocity matching condition to make a spectrally pure single photon source. So with such condition, use such pulsed pump, it is possible to demonstrate this QKD?
Not to my knowledge. That I don't think our proof does not apply to that because that pulse is too short.
So you use 50-50 beam splitter to do the measurement and also to generate the K and also get the security proof. Is it possible using about 10% to do the Franzen interferometer and
right?
90%
So
to get the K?
The Franzen, when you say 90 and 10%, you're talking about within the Franzen? No. Yeah. In fact, in the QKD protocol for the Franzen, it was 90 and 10. 90 go to key generation, 10% go to the security measurement. Yes. So that's to optimize the key a little bit.